Okay, first, bonjour. it, it's my pleasure to finally be here, and it's through the efforts of a lot of people that we were actually able to carry this out, and but it's because we believe that teachers are the pivot point in science, and what we should be doing here is reaching out to you and showing you the excitement, and hopefully get you excited because you're the ones that are going to transmit it to the public and to the students more than anyone else. And we think that's vitally important. But also, it's great fun for us to share the kind of exciting discoveries and things that we're seeing today. And so if the excitement isn't coming across, talk to us and find out what we're doing. We have postdocs and researchers, and usually have some students here, but one of my students has got to write his thesis, so he's a little bit. But just talk to us and get a feel for what's going on, how exciting the world of cosmology is today. So, and this is an experiment. You're the first, the pioneers, and you're a selected group because we couldn't, even though this is the first time, there were many people we couldn't accept. So we only did 20 people from each academy, and so we're hoping that you will learn and experience this. We're going to put on the web a lot of this material so that other teachers can have whatever we can glean from this. All right, we've had enough introductions, so I'll get into actually introducing cosmology to you, give you an overview, and then we can follow up with many talks after that. Okay, so we're doing what's like a detective story. That is, we've come across the scene after a lot of things have happened, and we're trying to reconstruct the entire, how the universe began and how it developed over time, just how the crime unfolded of how we got to be here today. And so that there are shows on television, which the English version of Cosmic is a crime scene investigation. We are using the similar kind of techniques to forensic scientists to try and reconstruct what happened at the beginning of the universe from the relics left over from creation, and also from other observations that we have in order to try and understand the whole sweep of the history of the universe. And so here's the Hubble Deep Field, which is one of the pieces of one of the relics that we have of the formation of the universe. Namely, when we look at this picture, we are struck by the fact that we see very few stars in this picture. There are only 4 stars in this whole picture, and actually a couple of them are cut off, so there's only 2 on the screen. And everything else in here are galaxies. Right? But the other thing that's interesting is, if you look, there are some big galaxies in here, this big spiral galaxy, a big elliptical galaxy, and a few others. They turn out, when they're big, they also turn out to be sort of yellow in color. Further away, we see small galaxies, and they turn out to be blue or blue-white. But we already know the universe is expanding, and the light from distant objects is shifted more to the red than the light from nearby objects. So it was a surprise to see the faraway galaxies being, bluer and therefore hotter than the nearby galaxies. So when we look at this picture, we immediately have a lot of questions. The first is, where did the galaxies come from? And we can estimate there are very many galaxies. This Hubble picture has a very narrow field of view. It's less than 1/40th the size of the moon. So if you extrapolate it to the whole universe, mapping it with the Hubble, you would see at least 100 billion galaxies. So the questions are, where did the galaxies come from? Why do you need 100 billion when obviously one galaxy is enough for life, right? One solar system is enough for life. So why 100 billion? And how do they change over time? We see faraway galaxies have more star formation, more things going on. Nearby galaxies look more like our sun, right? So we have questions right away from this picture, many things to try and explain, and we have a lot of evidence, a lot of pieces of the sky. Okay, so we have a primary tool that lets us hope to solve this problem, and that is that the universe is so big that even though the speed of light is large, it acts as an optical delay line. If we look out further, we see further back in time. So when we're looking at things in our solar system, light only takes a few hours from the most outside of the solar system. But from the nearest, say, 100 stars, light takes on the average 10 years to get here. So if I have a picture of Alpha Centauri, or a planet around Alpha Centauri, I'm seeing what it looks like 4.2 years ago. Typical stars in our galaxies are between 1,000 and 100,000 years in light travel time to get to us. But if you look at a nearest big galaxy, Andromeda, for example, it takes light 2 million years to get here. So if you had a great telescope and you were on a planet in Andromeda and you took a picture of the Earth, it would be a picture of the Earth 2 billion years ago. It would look very different than it looks now. There would be no lights from humans, no Great Wall, no evidence of humans at all because there weren't humans. But the planet, the planet looks pretty much the same continents and so forth, but a very different kind of environment. Well, the light from a typical galaxy will take between 100 million years and 10 billion years to reach us. And light from the very beginning of the universe, this outer shell, which Ken Ganga will talk about and I'll talk about a little bit, takes nearly 13.7 billion years to get to us. So if our job is to understand the universe, we can measure a set of spheres around us, and we'll have snapshots of the universe at different epochs. Right? So if we make measurements on spheres around us, then we have a time sequence lapse of how the universe developed. So to recap, we're in a spiral galaxy in a spiral arm. So we think about a series of spheres around us. We see near us sort of modern or present day galaxies. And if we look out further, we see galaxies that are more irregular shaped and have more star formation and doing more things. They haven't evolved yet into the more modern galaxies. If we use light, we have a set of cosmic spheres of time around us. So the beginning of the universe, shortly afterwards, and then the period when galaxies and stars form, and then more and more modern galaxies form. And all we have to do is measure samples of the universe at different distances away. We can measure samples of the universe as a function of time. Okay, so you will hear a little bit later about how we've been making observations. I've been spending a lot of my life making observations about the very earliest time in the universe we can see, both with the COBE satellite. Later we have WMAP, and then Ken will tell you about Planck, and I will show you some pictures of Planck, where we're making better and better quality maps of this early universe when putting a big amount of effort. But before I go to that, I want to show you some movies. The first movie was made in 1997. And it's about a researcher who is looking for signals from extraterrestrial intelligence and finds one, and it tells the machine how to make a machine to come and visit the extraterrestrials. So you get to travel through the universe. So this is the scientist, and there, of course, the Earth and the Moon, Mars, asteroids, the Galilean moon, and Jupiter. And this time we discovered the red spot was a giant storm, a cyclone. And the planets lined up nicely for the grand tour. So Saturn. And later you will see more asteroids in the Kuiper Belt. And then material, primordial material from the formation of the solar system, the Oort cloud. And now nearby stars. And this is one of the first Hubble pictures. And this is a place where new stars are forming. It's a big cloud of gas, dust, molecules. So this bright stars have blown the cloud apart so you can see in. It's a very beautiful tour. Jodie Foster is the one taking this trip. It's from the movie Contact. This is our galaxy. So nearby galaxy. You'll notice there's a lot of galaxies. Get to go through a couple of them. And she ends up in a room where the aliens talk to her. Okay, so the next movie is the one that we made a little more than a year ago, and it's based only on data. That one was data, but with production values and other material added. This one is based on actual data, and you'll understand the difference. So it starts from the highest point on the Earth, which is Mount Everest. From the highest to the lowest point on the Earth is 28 kilometers, and the Earth's radius is over 6,000 kilometers, 6,400. So the variation is only a part in 2,000, but you see the surface very irregular until you get away in space, and you see how smooth the Earth is, how close to a sphere it is. So it's a near perfect sphere. And the white diagonal here is geosynchronous, which is almost continuously inhabited by every satellite. Everywhere a satellite can be around there, it is. So there's the moon's orbit on the inner planets. So you'll note the distortion of the constellations as we get further away. So this is all data. And you see the cosmic variations that show up so many colors. They're at a level of a part in 100,000, so 200 times less than the Earth's variations. So. So the Earth is almost a perfect sphere, but the universe is even more perfect. So we make these pictures not only because they're pretty and they give us a nice way of understanding our place in the universe, but also because it is the way which we're going to try and understand what happened, how was the universe created, and what happened over its history, and try and explain everything we see and even project what may be happening into the future. Right. Be, being able being able to take the data and fly through the universe and fly around the Earth is very valuable in understanding both what's going on now, but also what went on in the history of the universe. So I want to talk a little bit more about the mapping. We're running a little late, and show you a little bit about how we collected the data on so many vast scales. Right? You know how we made maps of the Earth with satellites, but we've also used satellites to map the beginning of the universe and big ground-based telescopes to do some other things. Here's one of the things that Ken Ganga will tell you about after the break, and we'll try and show you a movie to launch. But here's a movie about how the sky was mapped. You put the satellite out to far orbit, get it cool and very sensitive, and just receive radiation coming from the sky. And as you scan around the sky, you begin to make a map of the sky. You see the plane of our galaxy showing up across here. This is actual first-year Planck data. So these observations are going on right now, even as we speak, and we're doing it because there's so much we can learn about the early universe. It only tells us not only what the conditions were like then, but tells us some information back earlier times and later times. So from the observations we have so far, we've made up a model of the universe. That is, if we consider that everything we can see is in a sphere whose radius is about 14 billion light years at the present time, and has modern galaxies in it, then we can take a slice through it and follow that slice back through time and see how it evolved right back to the beginning and make up a model of how that happens. And so the amazing thing is here we're extraordinarily large, 14 billion light years in radius, 100 million galaxies, and each one of them has 100 billion stars in it, until we go back to all of that was in a region that was smaller than an atom, and quantum mechanics was very important. Right? So we divide the universe into a series of epochs, and each epoch is relatively simple, although later it gets more complicated. We have the time when the light comes to us from the relic radiation from the beginning, the dark ages, the dawn of the universe, the first stars and galaxies forming, and then more modern stars and galaxies forming. So at about this epoch, our solar system is forming. And somewhere in that same rough time, but probably a little bit later, we find the universe, which has always been expanding, starts expanding more rapidly. Okay, so what we're doing is trying to measure slices through here to see this development over time, to make sure we understand what's going on. But we have models and simulations that we do to reproduce this and compare those against the observations we make. And we have had to do some amazing things. We had to invent inflation, right? So, and we had to have dark matter, and now we have to have the dark energy or something to cause the acceleration of the universe. These are things that we're able to calculate to sufficient accuracy now with simple models, but we know more complicated models have to be developed. It's exciting in that area. But the other area that's tremendously exciting is we're getting tremendously more data. That's what I was showing you in the maps. Okay. So we have here where we overlap with the CERN LHC, and then here we're seeing the relics, the run out of the kind of things that happened from the early universe. So it's not only the fact we're getting exciting observations looking out to space, but we're also going to get them from the LHC, we hope. So here's an example of a kind of a survey is going on where you saw the data before. There are a couple of sky surveys that went on. The Sloan Digital Sky Survey with 1 million galaxies. And every point on here is a galaxy. And it's taken like the Hubble pictures. You take a picture. It gives you a cone out in space. You look and find the position of each galaxy and estimate its distance, and you plot it on this graph. So as the Earth rotates, the cone gets stretched out to a fan. So here's a movie that shows the fans. The resolution is not very good, but you can see there are places where there are almost no galaxies and other places where there are large clusters of galaxies. And there's a feature here, which we call the Great Wall of Galaxies. So it's not just a string or a filament of galaxies, it's actually a sheet of galaxies. The next movie is a fly-through of another survey. So this is a large data set, again, about 1 million galaxies. And in each case, we have not only the galaxies, where they are, but we have information about each galaxy. Spiral, color, elliptical galaxy. You can see the geometry of the survey, again, the cone, just set by limitations of observing from the Earth. You can see voids, and you can see that. And here's another section of the Great Wall. But you can see they're not randomly put down, but there's complicated structure to how they formed. So right now, the data I'm showing you come from this little region. There's a second survey going on, which is Sloan 3. So that's Sloan 1 and 2. This is Sloan 3 that's now underway. And we have proposal in now to continue out. So 1 million galaxies, 5 million galaxies, hopefully 20 to 50 million galaxies, and 1 million quasars, where you measure the spectrum along the way. And so this is proposed, and in fact, next week, I'm at a review of this proposed. There's still a way to go to get back to where we're mapping and what Ken Ganga will tell you about. So we also do simulations we put in the primordial fluctuations measured by the radiation, and we let gravity take its course for billions of years. So you will see when we get down to zero and restart, the universe is very uniform, and then some spots appear, and then the spots come to make filaments. So spots appear, and then the spots connect to filaments. So this simulation is done with only dark matter. There are much bigger simulations done that include dark matter plus the ordinary matter. So I'll show you a movie of the plan view. This distance is 3 billion light years. So on 3 billion light years, the universe looks very uniform, but in close, it looks very complicated. So you see the filaments. The dark matter is in white, and the ordinary matter is in yellow, like the sun. And we're moving in on the intersection of many filaments where it's at least 100,000 galaxies in this cluster. Over 100,000. And this is the distance between us and Andromeda. So if we lived in a large cluster like that, we would see galaxies everywhere we looked with our naked eyes. It's much better to have a map than to fly through it. You see the white is the dark matter, and the yellow is where the stars have formed out of ordinary matter. You'll understand later, we think every galaxy is in a halo of dark matter that just can't collapse and relax the way the ordinary matter can. The ordinary matter is like dirt sediment in your bathtub. It goes to the bottom of the water. So it's more beautiful when you're flying through it, but it's much harder to understand what everything looks like then. So here's an illustration of both the structure formation and the time slice, the cosmic spheres of time, where we're talking about time back in billions of years, or millions, millare di anni. Early, the universe is warmer and more uniform, and slowly structure forms, and the structure gets more and more organized. Unfortunately, the resolution of the camera, the projector doesn't show it, but here you're starting to see the filaments we saw in the last movie. Here's the picture without the labeling on it, so you can see how smooth it is, how spots form, and then how filaments form up and then get tighter and tighter over time. So here is the early measurements. I don't know if Ken will show this, or will you show this one or not? That one. So this is the measurements from the COBE experiment, and then from WMAP. And if we had measured the Earth, you would have seen this with COBE, and you would see that with the resolution of Planck. And you'll see there's a huge difference between the way the Earth looks, the surface of the Earth looks, and the way the surface of the universe looks. And it actually tells us something about the nature of the forces. There are nonlinear forces shaping the surface of the Earth. There are almost no nonlinear forces or negligible nonlinear forces shaping space and time. So now I'm showing movies of what the raw data came from that movie made a little over a year ago was from. So here's starting at the sun and moving out, and you'll see what has come from the mapping of the location of 1/2 billion stars, so a lot of stars. So humans have managed to map the location of 1/2 billion stars, but even so, we have to go to French Impressionism to make the galaxy. There are 400 billion stars in the galaxy. We've measured 1/2 billion, so 1 in 800. And this is our local group of galaxies. You can see the new movie is much higher quality, but this is the original data put together in a couple of pieces. But you go a long way from our group before you start seeing more galaxies. So Jodie Foster got it almost right. So now more pieces of what eventually got made into that movie. The red are the large red luminous galaxies and the quasars. They're the ones you can see further away if you only have a small telescope. So this is what we've mapped so far. In here we've mapped fairly thoroughly in these slices. And out here we've mapped very well, but everywhere else we have much work left to be done. Okay, so we're back to this picture. We're still trying to measure enough in here to compare our theoretical models and calculation simulations against what we actually observe. And that's what we're right in the middle of doing and will be for the next 10 or 15 years at least.
Donc la question c'est, il semble que quand on voit les simulations, on est au centre de l'univers et que l'univers a une structure sphérique. Donc est-ce que c'est la réalité ou bien est-ce que c'est un artefact de la façon de présenter? So in the simulation, it seems that we are in in the center of the universe, and then the universe has a form of a sphere, and so that would be a question that a student would clearly ask after seeing this. So is it true, or is this just an artifact of the way this is presented?
So we don't think that we're necessarily at the center of the universe. We could be in a situation where all the points were equivalent. Around every point there's a sphere of things you can see. The reason we show things in a sphere is because we're using light come to us. We don't have a map of the entire universe from everywhere. We just use light coming to us to make our map. And the light comes to us and makes a series of spheres around us that we can see as we go back in time. And so if you actually look at the simulations as opposed to the pretty pictures I showed, some of the simulations are done as large cubes because calculationally that's easy to do. And a few of the simulations are done according to what we call the light cone. That is, you simulate the information you need in order to project back what you would see observing from the Earth. But in fact, there is no reason to believe that we're in a special place in the universe.
Donc on n'est pas dans effectivement dans une position particulière dans l'univers. on pourrait faire la même chose en n'importe quel point de l'univers. Je crois que ça a été montré, par exemple, dans le cas d'Andromède, où on vous a montré ce que serait la Terre vue d'Andromède. La seule chose, c'est que comme on fait des observations avec la lumière, donc on est biaisé de cette façon-là, puisque plus la lumière est ancienne, plus elle vient de loin. Mais donc on pourrait refaire la même chose en fonction de n'importe quel point dans l'univers. Donc il n'y a pas de place spécifique et on n'est pas au centre de l'univers, effectivement. Et cette notion de sphère vient simplement du fait que l'univers à une certaine époque donc est à une certaine distance et donc la même distance tout autour de nous. Alors, on le voit dans les simulations où certaines fois les simulations sont dans ce qu'on appelle le cône de lumière, c'est-à-dire qu'on voit à partir de la Terre, mais vous avez vu d'autres simulations où vous voyez de l'univers qui est représenté par une boîte, et nous, on est quelque part dans cette boîte. Donc la question, c'est la matière sombre, puisqu'elle est sombre, comment est-ce qu'on l'observe, et en particulier, est-ce qu'il y en a à côté de nous ou pas? So the question is about dark matter. Since this is dark, so how does one observe dark matter? And is there dark matter close to us?
Okay, so the question of dark matter is a good one, especially in France, where there's some people who are trying to modify gravity instead of having dark matter. We see dark matter the same way that Laverre inferred that Neptune existed. He saw the perturbations on the orbits of the planets inside, did a calculations, figured there had to be a planet, predicted where Neptune was within a degree. So what you assume in that case is the gravity is correct and that there's a perturbation, right? In this case, I don't have the curves. I can probably find them or they'll come up by accident. You can look at the speed of stars orbiting around our own galaxy, and you can see, instead of falling off from the center of the galaxy where it should be fast, because there's, just like Mercury goes fast and Pluto goes slow, you expect the velocity to fall off as one over the distance if all the matter is concentrated in the center, right? But in fact, what happens is the velocities of the stars actually are near zero at the center because it's going slow. It rises up, reaches a peak, what you would expect because the mass is concentrated there. And then it doesn't go down, it levels off, stays constant. That tells you there's more and more matter the further and further out you go. And what we believe is there's a halo of dark matter all around our galaxy, which is much bigger than our galaxy. Our galaxies collapse to a disk inside of a big spherical or spheroidal halo. And it's that way. And it's not just our galaxy. Almost all galaxies have this behavior. And clusters of galaxies have this behavior. Right? Large groups of galaxies orbiting each other have the same thing. So you want to try? Yes. And we can do gravitational lensing.
Donc, on voit la matière sombre un petit peu comme on a identifié certaines planètes avant de les observer. Par exemple, la planète Neptune, on a commencé par observer que les orbites des autres planètes, qui étaient, elles, déjà identifiées, étaient telles qu'il y avait la présence d'une masse quelque part. Et donc, c'est comme ça qu'on a d'abord identifier Neptune avant de l'observer. Donc ça, c'est la même chose ici. Ce qu'on regarde, c'est dans une galaxie, les trajectoires des étoiles. Par exemple, dans une galaxie spirale, vous avez des étoiles qui sont animées de certaines trajectoires, et comment ça varie en fonction de la distance au centre. Si vous aviez de la matière qu'au centre, c'est-à-dire que de la matière lumineuse, à ce moment-là, les étoiles qui sont assez lointaines autour de la galaxie tourneraient à une certaine vitesse. Voilà, vous l'avez ici. Donc ici, vous avez une galaxie. J'imagine que ça, c'est la partie lumineuse de la galaxie. Donc pour l'instant, vous n'imaginez qu'il n'y a que ça. Et voilà comment évolue la vitesse de rotation des étoiles au fur et à mesure que vous les éloignez de cette galaxie. Donc ça devrait évoluer comme ceci en fonction de la distribution de masse lumineuse que vous voyez. Et au fur et à mesure, la vitesse de rotation, vous êtes de moins en moins sensible et donc la vitesse de rotation est de plus en plus faible. En fait, ce qu'on observe, c'est qu'autour de cette galaxie, la vitesse de rotation des étoiles, quand on s'éloigne, c'est des distances de kiloparsec, quand on s'éloigne, vous voyez, continue à augmenter. Donc ça veut dire qu'il y a de la matière que vous ne voyez pas, et ça veut dire que cette galaxie est beaucoup plus étendue que prévu, parce que son effet s'étend à des très grandes distances. Et donc c'est à partir de ce qu'on appelle des courbes de rotation, justement, qu'on identifie effectivement la quantité de matière qu'il y a dans cette galaxie, simplement sur des principes de force gravitationnelle, la quantité de matière qu'il y a dans cette galaxie. Et donc on en déduit que, en fait, ici on ne voit pas, mais tout autour, là, il y a ce qu'on appelle un halo de matière sombre. Et on peut cartographier ce halo de façon à rendre ça compatible, hein, si on connaît la loi de la gravité, de façon à rendre ça compatible. Alors George, juste au début, a fait une petite remarque sur le fait qu'il y a certains physiciens français qui pensent que on peut expliquer les choses autrement. Là c'est en supposant que la loi de la gravité est absolument... enfin, et la loi qu'on connaît bien et que vous enseignez en classe, certains pensent que cet effet-là n'est pas dû à la matière sombre, mais dû à une modification de la loi de la gravité. Alors évidemment, donc il y a toujours ces deux possibilités. C'est aller chercher un petit peut-être, comment dire, c'est disons moins probable comme solution, mais c'est aussi une solution possible. Au lieu d'introduire de la matière cachée, vous pouvez aussi modifier la gravité à des distances galactiques pour essayer d'expliquer cet effet. Donc à ce moment-là, il n'y aurait que la matière lumineuse, mais la gravité serait modifiée. Et donc il y a un petit groupe de gens qui considèrent que c'est plutôt dans cette direction qu'il faut regarder. C'est de nouveau les données qui vont faire la différence. Donc la question c'est comment est-ce qu'on sait qu'une lumière donnée vient d'une distance donnée, de façon à justement reconstruire ces différentes échelles. So how do you know that light coming from a given source is coming from a certain distance? How do you reconstruct the distance?
Okay, so this is an interesting question, and for years we had to make up a thing called the cosmic distance ladder, which had 11 steps, where you measured the distance to nearby stars, which you could do by measuring their apparent motion as the Earth goes around the sun, and then measuring that, and then Hubble found variable stars and their brightness versus their period, and so forth. There's a huge series of steps that were done. Now we have more steps and more ways of estimating distance, but still there's a certain amount of uncertainty in that just because of how it goes. But one of the things we can use is gravitational lensing, where the light from a distant source gets bent around another galaxy or cluster of galaxies, and there's two paths or multiple paths, and the time delay is set by the geometry. And if there's a flare or outburst on one of the stars, you can measure the time distance, and that gives you another. So there are actually many different ways to estimate the distances, but what we do in general is estimate the distance by simply the redshift, how much the light is stretched, because that's the dominant change in wavelength. There's a little small perturbations, but just the redshift. For things that are very distant, things that are nearby, we have to estimate it more carefully. But there's a series of things. There is a certain amount of error in each one, and you just hope that they average out when you do the analysis.
Donc c'est effectivement une question complexe. En fait, la façon pendant longtemps avec laquelle on a procédé, c'est ce qu'on appelle l'échelle cosmique, c'est-à-dire qu'on va de proche en proche. Mais donc du coup, effectivement, si on fait une erreur dans un des... Donc ça veut dire quoi? Ça veut dire que, par exemple, on va regarder les étoiles les plus proches, et puis on va regarder leur mouvement relatif par rapport à notre propre mouvement dans le système solaire, et en regardant comment ça change au cours de l'année, on arrive c'est une mesure de parallaxe. Donc comme ça, on arrive aux étoiles les plus à identifier la distance des étoiles les plus proches. Après, Hubble a découvert des étoiles variables sur lesquelles on a fait un certain nombre d'hypothèses. Mais c'est vrai que pendant longtemps, c'est un grand débat parce que donc vous faites ça de proche en proche, mais si vous avez fait une erreur à un certain moment, évidemment l'erreur elle se répercute sur l'ensemble. Maintenant, on a des façons plus précises de mesurer la distance. Alors d'abord, il y a un grand principe qui est le décalage spectral. Vous savez qu'à cause de l'expansion de l'univers, donc les objets s'éloignent et donc il y a un décalage des raies bien particulières. Donc si vous avez la raie de l'hydrogène, la raie du carbone, la raie de l'oxygène, etc., vous allez voir décaler d'une certaine fréquence, vous allez les reconnaître, mais vous allez voir décaler, et en lisant ce décalage-là, vous allez donc avoir une information sur la distance à laquelle ça a été émis. Alors effectivement, mais le principal effet, alors là je réponds à la place de Georges, mais excusez-moi, mais c'est vrai, mais le mouvement, I'm answering instead of you. The question was, this is, the redshift is depending on the speed, on the velocity of the object. Oui. Voilà. Voilà. Oui, donc effectivement, il y a le mouvement local de l'objet qui émet, mais ça, c'est tout à fait négligeable. Le principal effet, c'est l'effet cosmologique, l'effet d'expansion de l'univers. Donc trouvé c'est la loi de Hubble qui vous dit que... Et donc c'est le principal effet sur le redshift. Donc il y a aussi d'autres petits effets sur la vitesse locale de l'objet, mais le principal effet, c'est simplement l'effet d'expansion de l'univers qui vous donne le principal décalage spectral. Donc la question c'est est-ce qu'on est en train simplement de prouver ce qu'on a mis dans le système, c'est-à-dire que on prouve l'expansion de l'univers en mesurant le décalage spectral. So the question is, isn't this a vicious circle, because you're saying that you prove the cosmological expansion by measuring the cosmological redshift, but you're assuming that the cosmological redshift is mostly due to the expansion of the universe.
It is a little bit circular. It's like arguing the gravity in this room comes from the Earth, right? There's clearly some from every person in here, but the Earth dominates. And so when you do the experiments and you drop, you put something on a pendulum or something like that, it swings and it stops pointing towards the center of the Earth. If you put a huge mass near it, it will be slightly off, right? So here we're looking and seeing what the effects are. And if you look at Hubble's early data, there definitely was some perturbation from the galaxies moving around. And you got a slightly different curve for individual galaxies or for clusters of galaxies where you group the galaxies in each cluster. But if you go to the great distances, there was one we swept through there. You go to great distances, the typical velocities are roughly 1,000th the speed of light for galaxies moving around, and yet you're seeing redshifts that are 1, 2, and 3, where the wavelength is being shifted not by 1,000th, but by a factor of 2. Right? It's a huge difference, right? I mean, it's not quite as bad as the pendulum and the Earth, but it's a big effect.
Donc la réponse, Georges compare ça au fait par exemple d'essayer de prouver dans cette pièce qu'on est tous soumis à l'attraction de la Terre. C'est quelque chose qui est un petit peu compliqué et donc par exemple il faudrait avoir une très grosse, parce que il faudrait par exemple avoir une très grosse masse dans cette pièce et montrer qu'il y a une petite variation qui est due au fait que cette masse-là va donc légèrement changer la façon dont les objets tombent. La réponse à la question, c'est que en fait c'est global, c'est-à-dire que effectivement, si on n'avait qu'une galaxie qu'on observe on ne pourrait pas en déduire si c'est l'expansion de l'univers ou un mouvement de cette galaxie. Mais cette loi de Hubble s'applique à l'ensemble des objets dans l'univers, et donc ça, c'est dans sa globalité que c'est vérifié. Et après, il y a des détails qui peuvent permettre de voir que, par exemple, en plus de cette expansion générale de l'univers, il y a des mouvements locaux qu'on peut mesurer. Bon, Jean-Yves rajouter un point.
Je crois comprendre la question. C'est en fait, là, ces questions, c'est quand on a mis une hypothèse au départ et qu'on la retrouve à la fin, on n'a pas avancé. Hein, ça s'appelle le paradoxe du bootstrap, c'est-à-dire comment se désembourber en tirant sur ses lacets. Hein. C'est un peu ça l'image classique, finalement, des raisonnements autocirculaires. En fait, l'expansion de l'univers est un phénomène observationnel. Pourquoi ? C'est parce que, comme ils ont expliqué tous les deux, en fait, on a une succession d'échelles de distance avec à chaque échelle ce qu'on appelle des chandelles standards, dont les distances ont pu être calibrées parce qu'on connaissait petit à petit les distances des échelons donc inférieurs. C'est-à-dire que c'est vrai que si on change l'étage, le rez-de-chaussée d'une maison, tout l'édifice se casse la figure. Hein. Donc c'est ce qu'il a dit. Or, pourquoi Hubble a vraiment déterminé que c'était une loi observationnelle ? C'est parce qu'il connaissait des échelons standards de lumière, ce qu'on appelle des supernovas ou des céphéides très brillantes, dans les galaxies proches. Et donc, connaissant les distances de ces galaxies et mesurant en même temps des décalages dans les spectres, on a pu établir une relation linéaire entre la vitesse et la distance. Et c'est ce qu'on appelle la loi de Hubble. V égale h fois d la distance. Hein, donc, constante de proportionnalité. Et l'histoire de la mesure des distances, c'est qu'en raffinant les mesures, petit à petit, on a affiné le coefficient de proportionnalité, qui est la constante de Hubble. Donc c'est cette linéarité pour les galaxies proches, relativement proches, jusqu'à 1 milliard d'années-lumière, qui est bien établie. Au-delà, on est obligé de faire des modélisations sur la structure, enfin le type de géométrique dans l'univers, est-ce qu'il est plat, est-ce qu'il est ouvert, etc. Ça devient plus compliqué. Mais cette loi, effectivement, est une loi observationnelle, établie.
Ok, je traduis. Oui, donc la question, d'abord en français. Puisque c'est durée limitée, donc l'émission du fonds cosmologique, comment est-ce qu'on peut expliquer, et que ça a mis un certain temps à venir ici, comment est-ce qu'on peut expliquer qu'on refait l'expérience 1 an après, 10 ans après, et qu'on obtient des données complémentaires du même phénomène. Donc comment on explique ça aux élèves? C'est ça un peu le... So the question is, if this comes from cosmic microwave background, cosmic microwave background comes from a slice of time. How do you explain to students that when you do the same measurement 10 years later, for example, from Kobe to WMAP or to Planck, you're seeing the same phenomenon and not something different?
Okay, and that's a good question. And it's partly because the universe is so big that the structures we see are much more than 10 light years thick. So 10 years is very small compared to the size of the things that we're seeing. And but the light comes from a certain epoch, right? But when we go further up in time, we're seeing out to a slightly further radius, right? So if we're seeing 13.7 billion years now, we will see 13.7 billion plus 10 years further out. But the structures are so large that we see basically the same structures. And so the light that we're seeing is not exactly the same light. I used to have a calendar I made for Kobe launch that showed the photons we were going to observe for the first 2 years approaching, through the galaxy towards, past Andromeda, past the Alpha Centauri and coming in and finally to Pluto and so forth. And you see this group of photons coming in, but there's another group of photons behind them coming from the same epoch, but from a little further away.
Oui, donc le point, c'est que les structures qu'on observe dans cette, du fond cosmologique sont beaucoup plus grandes que 10 années-lumière. Donc ça veut dire que même si on attend 10 ans, on va voir en gros les mêmes structures. Alors pas tout à fait, comme Georges l'a fait remarquer, imaginez que quand il a observé le ciel avec Kobe, il observait le ciel à 13,7 milliards d'années. 10 ans plus tard ou 15 ans plus tard avec WMAP ou Planck, on observe le ciel à 13,7 milliards d'années plus 10 ans. Mais les structures sont beaucoup plus grandes quand même que 10 années-lumière. Et donc, on observe à peu près la même chose. Il est vrai qu'on observe le ciel un tout petit peu plus profondément, puisqu'on a attendu 10 ans de plus. Donc, l'univers donc ça a repoussé effectivement un petit peu les limites. Mais les structures qu'on voit sont beaucoup plus larges que... on l'a vu d'ailleurs sur la carte entière du ciel. On a vu les fluctuations, elles sont relativement quand même grandes par rapport à la carte entière du ciel.